For decades, the world has been predictable. Models that explain everything from the birth of galaxies to the expansion of space were created by scientists, who were under the impression that they had discovered its deepest secrets. However, there is something that challenges our comprehension in the shadows. The James Webb Space Telescope, which is the most powerful human eyepiece ever made, has found phenomena that defy our preconceived notions. As universes structure quickly and space extends, the texture of our awareness starts to unwind. What if the world is not as we imagined it to be? What if the creation story is significantly more intricate and mysterious? Humanity's desire to comprehend the universe has always been the impetus behind astronomy. People have sought to understand their place in the universe by gazing at the stars since ancient times. The Lambda-CDM model, a framework that represents our best understanding of the cosmos, was developed in the late 20th and early 21st centuries, bringing this quest for knowledge to a conclusion. The standard planetary model, Lambda-CDM, is a significant advancement in astrophysics. According to this model, there is 68% dark energy, 27% dark matter, and 5% ordinary matter in the universe. It has provided responses to some of the most profound inquiries, such as, how was the universe created? What does it contain? What has changed over time about it? These inquiries, which have disturbed humankind for centuries, tracked down their responses in the exquisite conditions and hypotheses of the cutting-edge universe. The reasonable model depends on a mix of perceptions and hypothetical turns of events. The Big Bang theory, that the universe emerged from a hot, dense state, had its definitive confirmation when the cosmic microwave background was discovered in 1965. A unified model that illuminates the visible cosmos was created as a result of this discovery and advancements in the research of galaxy formation, the distribution of large-scale structures, and the rate of expansion of the universe. Einstein's general theory of relativity, which describes how matter and energy interact within the fabric of spacetime, serves as the foundation for the Lambda-CDM model. The universe began with the Big Bang approximately 13.8 billion years ago and has been expanding ever since, according to this model. The universe began as a boiling soup of particles. Matter began to coalesce under the influence of gravity over time as the universe expanded and contracted, resulting in the birth of the first stars and galaxies. Dark energy and dark matter, two enigmatic elements, are at the heart of the Lambda-CDM model. These beings are thought to make up the majority of the universe's content despite their elusive nature. However imperceptible, dull matter applies a gravitational impact that shapes the development of universes and the way of behaving of enormous scope structures. The formation and persistence of the galaxies we see today could not have occurred without dark matter. It is the unnoticed framework upon which the visible universe is constructed. On the other hand, the universe's rapid expansion can be attributed to dark energy. Dark energy drives the universe's accelerated expansion and counteracts the universe's gravitational pull, as shown by observations of distant supernovae. The disclosure of dim energy was quite possibly of the most astounding and significant advancement in present-day cosmology, proposing that the destiny of the universe may be altogether different based on what was recently envisioned. The large-scale structure of the universe, the formation and evolution of galaxies, and the observed acceleration of cosmic expansion are all explained in detail by the Lambda-CDM model, which includes dark matter and dark energy. It has established itself as the foundation of contemporary cosmology, guiding our comprehension of the universe and forming our expectations regarding its future. Astronomers and astrophysicists realized as the 21st century went on that they needed a more powerful observational tool that could go deeper into the universe and uncover the secrets of its earliest moments. Despite having revolutionized our understanding of the cosmos, the Hubble Space Telescope had some limitations, the most significant of which was its inability to observe the universe in the infrared spectrum with the necessary sensitivity and resolution. These limitations were addressed by the James Webb Space Telescope, JWST, which provided a fresh perspective on the universe. In honor of James E. Webb, a critical figure in NASA's set of experiences, the JWST addresses the climax of many years of mechanical development and logical desire. It is best known for its ability to observe the universe in infrared light, which enables it to see through cosmic dust and into areas of space that would otherwise be obscured by visible light. This ability is its most well-known property. Because the early universe's stars and galaxies are frequently covered in dust that reflects infrared light but blocks visible light, this capability is essential for studying their formation. The JWST is able to collect more light and observe fainter objects at greater distances thanks to the telescope's large, segmented mirror, which is made up of 18 hexagonal segments. The telescope can now see galaxies that formed just a few 100 million years after the Big Bang thanks to its increased sensitivity, providing a window into the very beginnings of the universe. The JWST has advanced scientific instruments that let it study the temperature, chemical composition, and motion of objects all over the universe in addition to its infrared capabilities. Astronomers can investigate the physical processes that control the formation and evolution of galaxies, stars, and planetary systems with the unprecedented detail provided by these instruments. Soon after its send-off and arrangement, the JWST started returning information that tested laid-out cosmological models. The discovery of galaxies that appeared to have formed much earlier and at a faster rate than the Lambda CDM model predicted was one of the most surprising findings. The telescope's deep-field observations of these early galaxies revealed unanticipated features, posing profound questions about their formation processes. The hierarchical structure formation theory predicted that the galaxies observed by JWST would be small, irregular collections of stars at this early epoch. Instead, they were massive, well-structured systems, some of which had features like central bulges and spiral arms that were supposed to appear much later in the history of the universe. Theories of galaxy formation and evolution that were in place before this discovery were seriously questioned. It suggests that our comprehension of these processes is incomplete if galaxies formed rapidly and reached such complexity in the early universe. The measurement of the Hubble constant, which is the rate at which the universe is expanding, is another area in which the observations made by the JWST have sparked controversy. There has been an increase in conflict between Hubble values based on measurements of nearby stars and galaxies, and those derived from observations of the early universe, such as those from the cosmic microwave background, CMB. This tension has been made worse by the high-resolution observations made by JWST. The discrepancies between various measurement methods have grown more pronounced, and the data suggest that the rate of expansion in the early universe may differ from previous estimates. Some scientists have speculated that the universe's expansion may be influenced by an unknown factor, which could point to new physics beyond the standard cosmological model. Dark energy and dark matter remain two of the universe's most mysterious aspects, posing some of the greatest obstacles to our comprehension of cosmology. In spite of their focal job in the Lambda CDM model, these substances presently can't seem to be straightforwardly noticed, and some inquiry whether our comprehension is finished or precise. A class of particles known as WIMPs, weakly interacting massive particles, is one of the primary candidates for dark matter. It is thought that the weak nuclear force interacts with ordinary matter, making it extremely difficult to detect these particles. WIMPs have been the subject of numerous experiments, but none have been successful to date. The axion, a hypothetical particle that has the potential to explain some observed phenomena in quantum chromodynamics, QCD, is another candidate. Axions could make up a significant amount of dark matter if they exist. Axions have been the subject of numerous experiments for their detection, but as with WIMPs, no conclusive evidence exists. Some researchers have proposed alternative theories that do not rely on the existence of dark matter because dark matter particles have not been detected. Modified Newtonian dynamics, MOND, is one such theory that suggests that the laws of gravity may alter on a large scale.